All right, today we're going to do something fun. We are cracking open one of the most common gadgets you'll find in any smart home to see what really makes it tick. We're talking about the humble smart plug. And trust me, by the end of this, you'll see the brilliant engineering hiding inside that little white box.
Think about it. You plug your lamp into it, you tap a button on your phone, and click, the light comes on. But how? How does that simple command from your app fly through the air into this device and safely control a really powerful electrical current? Well, that's exactly what we're going to break down.
Now, look, we all know what they do, right? They let us turn stuff on and off with our phones, set up all sorts of schedules, and maybe even keep an eye on our energy use. It's all about convenience, simple remote control. But that's just scratching the surface. The real magic, the part we're digging into today, is the engineering that makes all that possible.
To really get it, you have to think of a smart plug as having three separate systems all working together as a team. You've got the brain, which does all the thinking. You've got the muscle, which does the actual heavy lifting. And you've got the heart, which, well, keeps the whole thing alive. This simple structure is the key to everything. Because at its core, a smart plug is solving one giant engineering problem. You have this tiny, delicate, low-voltage world. We're talking 3.3 volts for a microcontroller that handles Wi-Fi and all the smarts. And then you have the high-voltage world of raw brute force power, the 230 volts coming straight out of your wall. The entire job of this little device is to safely bridge that massive gap. So first up is the brain. This is usually a tiny little computer chip called a microcontroller, something like an ESP32. It runs on just a few volts of power. Its whole purpose in life is to connect to your Wi-Fi, listen for commands from your phone, and make all the logical decisions. It's the smarts of the entire operation. Next up, you have the muscle. This part is called a relay. You can literally think of it as a remote-controlled light switch. See, the brain is way too delicate to handle that high voltage from the wall, so instead, it just tells the relay, the big, strong muscle, to do the heavy lifting of physically connecting or disconnecting that powerful 230-volt currents. And finally, the heart. But wait a second. How does that tiny, low-voltage brain even get power when it's living inside a high-voltage device? That's the job of the power system. It takes that dangerous 230 volts AC from the wall and carefully steps it down to the nice, clean 5 volts DC that the brain needs to function. It's the life support system for the whole plug. And this brings us to the absolute golden rule of this whole design: electrical isolation. That little brain, the ESP32, would be instantly fried. Poof, gone, if it ever came into direct contact with the wall's current. This one principle is the entire reason we need these three separate systems in the first place.
Okay, so we've got our three concepts down: brain, muscle, and heart. Pretty simple, right? Now let's meet the actual hardware heroes that play these roles inside a real smart plug.
So here's the cast of characters. The ESP32 microcontroller, that's our brain, doing all the thinking and talking on Wi-Fi. The relay module, that's our muscle, the big switch. And the AC to DC power module? Yep, that's our heart, converting the power. See? The concept maps perfectly to the physical components.
But having the right parts is just step one. Now you have to bring it all to life with software and, this is the most important part, make sure it doesn't, burn your house down. This is where the logic and safety design become absolutely critical. Okay, here is a fundamental safety rule in electrical engineering. You only ever switch the live wire. The neutral wire just passes straight through to whatever you've plugged in. The relay acts like a gate, but it's only opening and closing the path for that one hot or live connection. This is non-negotiable for safely controlling AC power.
So what about the software? Is it some super complicated code? Not really. At its very core, it's amazingly simple. When the brain wants to turn the plug on, it just sends a tiny high electrical signal from one of its little pins. That's it. That one little digital pulse is all it takes to command the relay's muscle to slam the high voltage circuit shut. A tiny command with a very powerful result.
And this really highlights the massive difference between a fun weekend project and a real commercial product. A professional device adds layers and layers of protection. A fuse in case of a power surge, a special fire-resistant plastic for the box, and better isolation using something called an opto-isolator, which actually uses a beam of light to send the signal, creating a physical air gap that electricity can't jump across. These are the details that earn those all-important safety certifications.
So, knowing all this, how does a company actually take these principles and turn them into a real business? Let's take a quick look at that journey from a cool idea to a product you can buy off the shelf. First off, what do you think it costs to just build one? The answer might actually surprise you. The core components for a working prototype are pretty cheap, around 1,000 rupees, which is maybe 12 US dollars. This incredibly low barrier to entry is what's fueling so much of the innovation we're seeing in the whole Internet of Things space. But going from that one prototype to thousands of units is a huge journey. You start with a messy prototype on a breadboard just to prove it works, then you design a sleek custom circuit board, put it through grueling safety tests, develop all the software and the app, and then you have to get official certifications before you can even think about mass manufacturing. So when you look at it, a simple, smart plug isn't really simple at all. It's this beautiful intersection of all these different fields. You've got embedded systems for the brain, serious electrical engineering for the muscle and heart, networking for the Wi-Fi, software development for the logic, and tough safety design protecting everything. And remember, this blueprint, this model of a low-power brain safely controlling a high-power muscle, it's not just for plugs. It is the foundation of countless smart devices, from your thermostat to your light bulbs. So now that you know exactly how it works, the only question left is, what would you make smart?